Hello everyone. In this session, let me explain one more important topic as per the exam point of view. It is called as singularity. So as this question is asked so many times, so you have to understand the concept. Anyhow, I will forward the definitions of the same. So coming to the singularity, first let me explain the concept of singular point. Fine. Suppose if you have a point, say z is equal to a in a complex plane. So, if this point is said to be a singular point only when this point fails to satisfy analytical condition. In the sense, when do we say a function f of z is analytical? Only when it is differentiable at a point and at a point z and also in its neighborhood. Then we can say f of z is differentiable, right? I mean f of z is analytical. Right. Similarly, we say this point z is equal to a is a singular point only when this point fails to satisfy analytical condition. I'll give you one example. Suppose if I am going to consider a function f of z as 1 by z. Right. Suppose if you are going to give z is equal to 0, this value is not defined, right? Then we can say z is equal to 0 is the singular point. Is the singular point of a function f of z. Similarly, suppose if I have a function, say f of z is equal to 1 divided by z minus 1. So here z is equal to 1 is a singular point. Fine. So if you replace z is equal to 1, this function value not defined. So we say z is equal to 1 is a singular point of this function. So example, this is first example, this is second example. I will give you third example. Let us consider a function f of z as 1 divided by sin z. So if you are going to give z as n pi, so as I already told you, sin n pi value is 0. So 1 by 0 will be infinity. So this function is not defined. So z is equal to n pi is a singular point. So a point z is equal to a is said to be singular point of a given function f of z only when it fails to satisfy a condition of analyticality. Or it is not analytical if a function f of z is in a complex plane, then if you are going to calculate f of a which is not analytical, then a is called as a singular point. Fine. Now next concept is we say it is a isolated singularity. It is one of the type of singularity. So isolated singular point. Fine. It can be defined in 2 or 3 ways. A singular point z is equal to a. We say a singular point. First of all, this point should be singular point as it satisfies. It failed to satisfy analytical condition. It become a singular point. So a singular point z is equal to a is said to be isolated if neighborhood of z is equal to a contains no other singular point. In the sense, suppose if I have a complex plane, if z is equal to a is one of the isolated point. If there is no other points around this a such that it is singular point. In the sense, I'll just repeat the statement, you just listen to me. The singular point z is equal to a is said to be isolated if the neighborhood of z is equal to a. In the sense, just beside and around a there is no singular point, then z is equal to a is called as isolated. Isolated in the sense separate singular point. That's all. And one more definition we can say is if f of z is analytical in a disk, say 0 less than mod z minus a which is less than epsilon for some delta greater than 0 and which is not analytical at z is equal to a, then z is equal to a is called as isolated singular point of a function. So I can give the same example. Clear? And further functions like root 2 log z, multiple functions, the concept of isolated singularity is not applicable for this kind of function, whereas it will be applicable for the functions as I given. No example, f of z is equal to 1 by z, 1 by z minus 1, 1 by sin z, and sin z by z, and e power of 1 by z, cosecant 1 by z, 1 by sin 1 by z. So all those functions, for all those functions, isolated singular point will be applicable. Fine. Now the next concept is classification of this isolated singular point, and it is very important. So in isolated singular point, I think you are familiar. You might have clear with the concept of isolated singular point as it is one of the singular point. Again, this isolated singular points can be classified into 3 types. First one is removable singularity. Removable singularity. Second one is pole. We say it is a pole. And the third one is we say it is essential singularity. essential singularity. Further, you have very important theorems and problems based on this concept. So in isolated singularity you have three types. First one is removable singularity, second one is pole, and third one is essential singularity. Now let me explain the concepts in detail. Now the first concept is removable singularity. Type of us isolated singular point. It is a removable singularity. If you go through the question paper, you can see a number of questions based on this concept. So removable singularity we can define in three ways. Anyhow, I'll give you all in notes, so you have to write all in exam. Fine. Please don't skip any of the definition. Fine. So removable singularity in the sense, suppose if I have a point A, which is isolated singular. So removable singularity is a type of isolated singularity, as I said. Suppose if I have a point A which is isolated singular point, then we call Z is equal to A is a removable singular if there exists another analytical function. Let me take that analytical function as g of z in a disk. Disk is mod z minus a is less than r, right? So disk equation. So here I am going to consider mod z minus a is less than delta, such that f of z is equal to g of z for z not equal to 0. This is one of the definition. I'll just repeat once again. An isolated singular point A is said to be removable singularity if and only if there exists another analytical function g of z in a disk mod z minus a less than delta, such that which satisfies the condition f of z is equal to g of z. So this is one definition. And one more definition is that an isolated singular point z is equal to a is said to be removable singularity if the principal part in the Lorentz series expansion is absent. In the sense where, as you notice that whenever we expand the Lorentz series expansion, we are going to get two terms. That is one for minus infinity and another for like z minus a power of n, plus another for plus infinity. While solving the problems, I have explained n number of times. One part is principal part, another part is analytical part, right? So in that expansion, Lorentz series expansion, if the principal part is not there, if the principal part value goes to 0, then such kind of expansion is called as such kind of point is called as removable singularity. I'll just define this definition once again. The isolated point z is equal to a is said to be removable singularity if the principal part in the Lorentz series expansion is absent. So if you expand that function about that particular point, principal point should goes to 0, then we can say given point is removable singularity. I'll give you one example. Let me take one function f of z as sin z by z. So if you apply Lorentz series expansion for this, you will get, you already know the expansion for sin z by Taylor's theorem. It is z cube by 3 factorial. That is, you are going to get add numbers here. Alternatively, negative and positive. For cos, you are going to get even numbers with positive sign, right? When you are going to multiply it with 1, z square by 3 factorial plus z power 4 by 5 factorial, so on, you will get, right? So if you are going to substitute z is equal to 0, this analytical part, this principal part will be 0, right? Only analytical part will remain for you. I mean z, the term containing z will goes to 0 around the point z is equal to 0. That is, principal part of a Lorentz series expansion goes to 0. Then z is equal to 0 is called as removable singularity of the function f of z. Clear? Further solving the problems procedure is different. You just understand the concept just for exam point of view. Fine. So if z is equal to 0, that principal point goes to 0. So such kind of point is called as removable singularity. This is the first kind of isolated singularity. Next definition is pole. So pole is none other than, suppose if I have a point z is equal to a, we say this is a pole only when it satisfies the condition limit z tending to a magnitude of f of z is equal to infinity. A point z is equal to a in a complex plane is said to be pole if it satisfies this condition, that is limit z tending to a f of z is equal to infinity. Further, we have two types of poles. See here, in isolated singular point we have removable pole and essential singularity, and again in pole you have two types. It is pole of order m and simple pole. We can define, depending upon the order of the pole, we can also define double pole also. Fine. See, in exam if the question is given only for the limited mark, not only in my subject, on almost all the subject, you have to express the content as much as you know. So if they asked you to write the definition of isolated singular point, it is better to explain all these three types. So if it is asked for 5 marks, it is better to explain types of pole as well, then only you will get full mark. Fine. So a point z is equal to a is said to be pole of order m if the principal part of f of z contains m number of terms. As I already told you, when you expand Lorentz series, you will get negative terms, no? Minus infinity to some values minus n, a n to z minus a power of n. So this term is referred to principal part. Fine. So if this principal part of f of z contains m number of terms, then it is called as pole of order m. Suppose if this principal part contain only one term, then it is called as simple pole. Suppose if principal part contain two term, it is called as double pole. So that is one definition. Second definition is, you have to write both the definition. So an isolated singular point z is equal to a is called pole of order m only when, if this definition is very important, you have to remember and you have to write the same. If z minus a power of m into f of z is bounded in its neighborhood. Neighborhood in the sense, suppose if I have a point z here and z naught here, z is a neighborhood of z naught and z naught is a neighborhood of z. Fine. So a point z is equal to a is called pole of order m if z minus a power of m into f of z is bounded in a neighborhood of the point z is equal to a. And if this value is bounded in its neighborhood, then we say z is equal to a is a pole of order m. Fine. Then we can define a function f of z as g of z divided by z minus a power of m, where g of z will be analytical at the point z is equal to a. Fine. Here you may get confusion. As I already told you, singularity in the sense the function should not be singular, analytical, right? Then only we say that point is singular. Now definition of pole says that an isolated singular point z is equal to a is said to be pole of order m if this condition, that is z minus a power of m into f of z, is bounded in its neighborhood of the point z is equal to a. If f of z is a pole of order m at z is equal to a, then there exists a function f of z is equal to g of z divided by z minus a power of m, where g of z will be analytical but not f of z. Since we are talking only about g of z, analyticality of only g of z but not f of z. If g of z is analytical at z is equal to a, then such point is called as pole. And simple pole, I'll give you one example for pole. Suppose if I have f of z is equal to e power of z by z cube. When you put z is equal to 0, we will get a pole, and this is called as pole of order 3. Clear? I'll give you one more example. Suppose I have a function 1 by z. So z is equal to 0. It is a pole of order 1. Fine. Suppose if I have a function like f of z is equal to sine hyperbolic z divided by z power of 5. If z is equal to 0, we say it is a pole of order 5. Why? Because z power is 5. So it is a pole of order 5. Hope so pole concept is clear. So that is the second type of isolated singular point. Now the third one is essential singularity. Essential singularity in the sense, suppose if a point z is equal to a is said to be essential singular point of f of z if principal part of a function contains infinite number of terms. So as I already explained, principal part in the sense if f of z is expressed in terms of negative terms. No? So this part is called as principal part. If this principal part contains infinite number of terms, then we say that point z is equal to a is essential singularity. Or we can say one more definition, that if a is an isolated singular point, why? Because it is a type of isolated singular point. Fine. So if a is an isolated singular point and a is neither a pole nor removable singularity. Fine. It should not neither removable singularity nor pole. If it is not both the case, then we can say it is essential singularity. Or a point is said to be essential singularity if the principal part contains infinite number of elements. Both the definition you can say. Clear? So this is the types of singularity. And we have one important theorem based on the singularity. We say that is Reiman theorem. Sometimes we say that as behavior of an analytical function. So here is the theorem. Hope so it is visible for you. Behavior of analytical function in the neighborhood of isolated essential singularity. So just now I have told you essential singularity in the sense principal part contains infinite number of terms, or in a point z is equal to a, which is neither removable singularity nor pole, is called as essential singularity, right? Now in one of the year only this statement is given. So this theorem decides a behavior of analytical function in the neighborhood of isolated essential singularity. This is one of the important theorem. You have to memorize this. Please practice this theorem. Fine. Now coming to the statement, if f of z is analytical, having an isolated singularity at z is equal to a, if z minus a is bounded in at z is equal to a, comma, if z minus a is bounded in the neighborhood of region, the disk 0 less than z minus a less than r, then f of z has a removable singularity at z is equal to a. So this is the theorem we need to prove is. Since in the statement itself it is clearly given that f of z is analytical and it has singularity at z is equal to a, right? So all these statement, whatever I am explaining I'll be giving the same in notes, but only steps I'll explain here. Since it is given that f of z is isolated singularity at z is equal to a, and moreover f of z is analytical, right? So if that was the case, we can expand the given function using Lorentz series. So let me write it. We can expand using Lorentz series. So I can write by Lorentz theorem, by Lorentz series, we can write f of z as n is equal to 0 to infinity an into z minus a power of n plus n is equal to 1 to infinity bn into z minus a power of minus n. So let me consider this as 1, where bn we have to write, where bn is given by 1 by 2 pi I into integral over c f of w into w minus a power of n minus 1 into dw. It is one of the application of Lorentz theorem. So if a function is analytical and if it has an isolated singularity at z is equal to a, we can expand Lorentz series something like this. Fine. Now let me choose rho, function rho in such a way that rho will be in between 0 and r. And let us consider a circle C or a curve C. Let it be circle. Let us consider a curve C. Let it be circle. And we know that circle equation is given by mod z minus a is equal to r. We have chosen rho in such a way that rho will be less than r, but it will be greater than 0. In the sense it should be positive. So I have considered the circle equation. Then let me write the bn as, I'll just write bn once again, 2 pi I into integral over c f of w into w minus a power of n minus 1 into dw. Fine. Now let us consider magnitude of this value. I'll just take mod on both sides. Remember, in PG, not only my subject, in all the subjects I'm telling you, don't skip any step. Try to write maximum, and presentation should be clean and neat, then only you will get mark. Fine. Now I'm going to split the modulus here. So when you split the modulus, equal sign will become less than or equal to. So I'll put less than or equal to, and you already know that modulus of 2 pi I is 2 pi. Modulus of I is 1. So I can write this as 1 by 2 pi integral over c modulus of f of w into modulus of w minus a power of n minus 1 modulus of dw. Right. Now 1 by 2 pi as it is, since f of w is bounded. Why? Because it is given that function is bounded. So let me take that bounded value of a function as less than or equal to m. So if any function is bounded, no need to write this condition. Clearly you can write it as m. Integral over c m. Now w minus a is a circle which is of radius rho. So I can write rho power of n minus 1. Then dw, see here, if rho is a circle equation, then dw will become rho into d theta. Rho into d theta. Clear? Now dw can be written as rho into d theta. So let me take constant outside. So you will get m into rho power of n minus 1. This step I have simplified n number of times. You just go through the previous videos. So rho into d theta is, since it is a circle, I have taken it as limit 0 to 2 pi. I'll just write one more step, d theta. So I can write this as magnitude of bn is less than or equal to 1 by 2 pi into m into rho power of n minus 1, rho as it is. Now d theta upper limit is 2 pi. Fine. into lower limit minus lower limit is 0. Theta you are going to get, rho is again a constant, anyhow you can write like this. So which is less than or equal to 1 by 2 pi into m into rho power of n minus 1 plus 1, right? Minus 1 plus 1 get cancelled, so you will get magnitude of Bn is less than or equal to 2 pi into m into rho, rho power of n. Clear? Again into 2 pi I have 2 pi minus 0 is 2 pi, so 2 pi get cancelled, anyhow I'll simplify here. So magnitude of Bn is less than or equal to m into rho power of n. Now you can note that as n tending to 0, as n tending to infinity, when you increase the values of n, rho will tend to 0, as you already done this concept in radius of convergence. So as you increase the values of n, rho will tending to 0. So with this I can write Bn tending to 0. So if Bn tending to 0, I can rewrite equation 1 as, so with this equation, hope so equation 1 is visible for you. So equation 1 becomes f of z is equal to n is equal to 0 to infinity an into z minus a power of n. Now you can note that, as I already told you in a Lorentz series expansion, first term stands for analytical part, this term that is minus power n stands for principal part. Right? Now you can note that in equation 1 there is no principal part. So if principal part is absent, therefore principal part is absent. So if principal part is absent, what can we say? As I already told you, if principal part is absent, it is removable singularity. Right? Hence, definition of removable singularity is a point z is equal to a is said to be removable singularity if the principal part is absent in a Lorentz series expansion. See the Lorentz series, we don't have a principal part here, it is with reference to negative powers. So there is no principal part here. So f of z is removable, f of z is removable singularity at z is equal to a. Hence proved. And that is what we need to prove. We see here, we have to prove that f of z has removable singularity at z is equal to a. So this is the required proof, and it is very important theorem. Please practice the same. So whatever the singularity I have done in this session, singularity is also asked for in so many years, and this theorem only statement is asked, so you have to practice this theorem. It gives the behavior of an analytical function in the neighborhood of an isolated essential singularity. Hope so it is clear. So next concept will be continued in the next session. Thank you.